Hello. Next section, chapter 5, is orbits. We've got to be able to recall Kepler's laws of planetary motion. So there's 3 of those. Solve problems involving Kepler's third law. That's the only one that has a formula. And recall that Kepler's third law can be derived from the relationship between Newton's law of universal gravitation and uniform circular motion. So that's what it says. Oh, that's terrible. All right, back here. That's what it says in the syllabus. There's only one formula here. T squared over r cubed equals 4 pi squared g over m. Right, it's a really quick little chapter. Kepler's laws of planetary motion. So his first law, all planets move about the sun in elliptical orbits, having the sun as one of their foci. That's a maths thing. So that means if this is the sun, it would be at the focus here, or the sun might have been at the focus there. So round it goes. That's the first one. There's a little bit of Greek on how it's called. Helios meaning sun, peri meaning around, so perihelion, aphelion, I don't think that really matters. Kepler's second law is the law of areas, which is interesting. So in the same time period, so say this took, for argument's sake, 2 days, this would also take 2 days, and those areas are equal. So the second law is the law of areas. A radius vector joining any planet to the sun sweeps out equal areas and equal lengths of time. So radius vector will sweep out an equal area anywhere in that orbit, right? So anywhere in equal periods of time. So that means that the speed must be changing. Excuse me. So out here, it's going slower. In here, it must be going faster. The third law is the one that has some formulas in it, and it's about the relationship between period and radius. So t squared is directly proportional to r cubed. So if we're graphing r cubed t squared, so t squared against r cubed, we're going to get a straight line. So a straight line is a constant, slope is a constant. So this would be a situation where you had information about one planet and then part of the information for a second planet. You could do a directly proportional ratio thing like this. So say you had the period and the radius of Earth's orbit, but you only had the radius for Neptune. What's the period for Neptune? So you set it up like this, because this t squared over r cubed is a constant. They've got a table down the bottom here where it shows you it's pretty close in real life. Real life's not always perfect, but it's pretty close to being. Kepler's ratio, it's called, a constant. So just like I just said, here we go. We've got 2 moons on Neptune, and it gives you 3 pieces of information, and you have to find the 4th one using that ratio. So that's easy enough. Now, it specifically says in your syllabus that you have to know that this rule, Kepler's third law, t squared on r cubed equals 4 pi squared on gm, and that is derived by saying the gravitational force and the centripetal force must be equal. All right, so by combining, you need to know that by combining these 2 rules, the gravitational force and the centripetal force, you can derive Kepler's third law. It says recall that Kepler's third law can be derived from the relationship between Newton's law of universal gravitation, that's this one, G equals mm over r squared, and uniform circular motion, mv squared over r. Right, so to combine those two together to get Kepler's third law. It doesn't say you have to prove it, it just says you have to know that it comes from that. So you'd have to be able to recognise this rule as gravitational force and this one as centripetal force, and know that they combine to give you Kepler's third law. And that's all there is to chapter 5. It's not a very big chapter at all.